This presentation provides an overview of the Load Observer feature, which is available in modern servo drives from Rockwell Automation. A number of questions related to motion system tuning, the auto-tune test, and the Load Observer feature will be answered in the following slides. First, the need for motion system tuning and the associated challenges will be explained. Then, the traditional auto-tune method for simplifying motion system tuning will be described. Next, the circumstances in which the auto-tune test is effective will be outlined, as well as when additional tuning methods must be utilized. Then, the new Load Observer feature for simplifying motion system tuning and 3 key benefits of using Load Observer will be examined. Finally, a consolidated summary of the Load Observer function, its benefits, and where to find technical information will be provided. So why is motion system tuning necessary? Closed-loop servo systems require settings for the control loop gain and filter values in order to ensure that the load accurately follows the desired input command signal. The process of adjusting and refining the gain and filter configuration is called tuning. The optimal tuning settings depend heavily upon the system characteristics. Each machine behaves differently due to variations in compliance, backlash, changing inertias, manufacturing tolerances, and machine degradation, just to name a few variables, so the tuning configuration can vary drastically from one machine to the next. Tuning methods and tools, such as the auto-tune function, currently exist to simplify the tuning process. However, the wide range of application types makes it very challenging to develop a simple, all-encompassing method for tuning. As a result, when the auto-tune function provides unsatisfactory results, manual tuning must be used, which often requires knowledge of advanced tuning techniques. In addition, manual tuning is applied to each axis independently, so each axis acquires a different tuning configuration. One feature that has traditionally been utilized to simplify the tuning process is the auto-tune function. When used, this function calculates the combined motor and drive characteristics and then calculates and sets the control loop gains. These gain calculations are strictly a function of the drive and motor characteristics and were optimized for rigid loads and high dynamic applications with rigid load ratios of 10:1 or less. For this reason, in the past, customers were generally advised to limit load ratios to 10:1 or less and to minimize compliance in their mechanical designs. The auto-tune function also performs a physical bump test that quickly measures the load ratio of the system. This load information is then used to set the dependent axis parameters, including the dynamic limits for the axis. In certain applications, the auto-tune technique is quite effective and does not require advanced tuning experience to utilize. However, the fixed set of equations that the auto-tune function uses to set the gain values is optimal for rigid, non-changing loads and for high dynamic applications with rigid load ratios of 10:1 or less, which comprise roughly 10% of applications. Applications which do not meet these conditions require additional tuning techniques if the auto-tune gains do not provide satisfactory performance. Specifically, systems with significant compliance, variable loads, or those needing a high level of performance may require additional tuning methods or tools. When the Load Observer function is enabled, it operates in real time while the machine runs. During machine operation, the Load Observer function estimates the torque required to move the mechanical load and provides a feedback signal to cancel its effect. The result is that the motor behaves as though it is unloaded, which is easy to control. The Load Observer feature alone is effective in roughly 80% of applications, as opposed to the 10% for the auto-tune feature. Load Observer works well not only for rigid loads, but also for compliant loads and systems in which the load varies either predictably or unpredictably. Since the Load Observer feature causes the motor to behave as though it is unloaded, the design recommendation to target a load ratio of 10:1 or less no longer applies. Some applications exhibit a mechanical resonance which can be eliminated with a notch filter that is simple to configure. When used in conjunction with the notch filter, the Load Observer feature is effective for 95% of applications and eliminates the need to hire or train an expert. The remaining 5% of applications require additional tuning for peak performance. Let's take a look at several key benefits of the Load Observer feature in more detail. Load Observer enables effective tuningless operation in many applications. In the past, prior to Load Observer, it was recommended to perform the physical auto-tune test on all axes when feasible. If the auto-tune test gain settings resulted in unsatisfactory performance, manual tuning was required. Now, with Load Observer, there is no need to perform the auto-tune test or manually tune most applications. This means that in many cases, there is no need to connect to the machine to commission the axes. In addition, a consistent configuration can be utilized not only across axes, but also across machines. Load Observer also effectively manages compliance in mechanical systems. In the past, prior to Load Observer, systems with compliance were often very challenging to tune. In many cases, performance was sacrificed in order to avoid unstable behavior due to disturbances during operation. Additionally, to compensate for the challenges faced with controlling compliance systems, machine designers were pushed to minimize compliance in their designs, which can be difficult and in some cases impractical. Now, with Load Observer, compliance systems can be effectively controlled without having to compromise on system performance or robustness to physical disturbances. In addition, machine designers can ease requirements to minimize compliance in machine designs. Finally, Load Observer provides simple control for variable loads. In the past, advanced techniques were utilized to control variable load applications. Specifically, complex gain scheduling and/or extensive programming was required to dynamically vary the control loop gain settings as the mechanical load varied. These techniques work when the load varies in a predictable manner. However, they are ineffective when the load variation is unpredictable. Alternatively, the control loop gains were set for the lowest inertia value in order to avoid instability as the load increased. This technique results in a sacrifice in system performance during higher inertia operation. Now, with Load Observer, the torque signal is automatically adjusted as the load varies. As a result, from the control perspective, the system appears as though it is unloaded, so the gain values remain constant throughout the operation of the machine. This also means that effective control is maintained even when the load varies in an unpredictable way. To summarize, Load Observer is a feature that drastically simplifies tuning in the vast majority of motion systems. It works by estimating the torque required to move the load and then applies a feedback signal to cancel its effect. As a result, the motor behaves as though it is unloaded. The key benefits of the Load Observer feature include tuningless operation for many applications, effective control of compliant loads, and simple control of variable loads. For additional technical information on Load Observer and tuning techniques in general, refer to the Motion System Tuning Manual on Literature Library.